Well, good morning, chemistry students. It's finally the big day. We're going to talk about moles today. I can define the mole as a measurement of quantity in chemistry. I can perform mole conversion calculations. So, all right. In chemistry, a mole is not some hairy spot on your chin. Okay? It is not just a little furry animal in the ground, although we do use it as a mascot. I don't know if you've seen this little guy. Here's a little mole wearing a lab coat and goggles. Okay. Former student of mine gave that to me. Pretty cool. That's a mascot. No, a mole in chemistry refers to a quantity of matter. A mole, one mole, contains the same number of particles as there are atoms in exactly 12 grams of carbon-12. Now, when I say exactly 12, I mean 12.0000000. Exactly 12 grams of carbon-12. So if you spent the next trillion lifetimes counting how many atoms were in 12 grams of carbon-12, you'd come up with a mole. Now, it's a big number. To 4 sig figs, and it's been measured a lot more accurate than that, but to 4 sig figs, 6.022 times 10 to the 23rd particles. And that number is known as Avogadro's number, who was a mathematician and chemist. Okay? If you wrote that out, that's a really awkward number. I mean, that's a lot. It's huge. It's mind-bogglingly huge. Okay? In talking to students over the years, some examples that you get, I said, what if you had a mole of pennies? If you had 6.022 times 10 to the 23rd pennies. Well, I did some measurements where I measured the volume of a penny, and then I multiplied by a mole, and then I divided by the surface area of the Earth, and I found out the entire Earth would be buried about a quarter mile deep in pennies, about 400 meters deep in pennies. The entire Earth. That's how big that number is. And yet, for water, I have, more than 4 moles, probably about 4.5 moles of water molecules just in this test tube, or this graduated cylinder right here. Atoms and molecules are really, really small. Okay? And there's a lot of them. The way we use a mole in chemistry is a lot like we use the word dozen in other things. So a dozen always refers to 12. Okay? At home, got cartons of dozen eggs in the refrigerator. Okay? You might buy a box of pencils, and it comes a dozen pencils sometimes. I have bought, a package of 72 pencils. 6 dozen. That's a half a gross. A gross is a dozen. Let's see. Eggs, pencils, students, donuts. We could have a dozen of any of those. Okay? So where a dozen always refers to 12, no matter what the context is, a mole always refers to 6.022 times 10 to the 23rd particles, no matter what we're talking about. So I could be talking about molecules, atoms, ions, etc. Formula units. All right. So let's hit the map here. Here we are. We got some islands. Here's Mole Island. Here's Mass Island. Here's Particle Island. I hear that there's several tribes running around on Particle Island. Atoms. There's the atoms tribe. There's the molecules tribe. There's the formula units tribe. There's the ions tribe. They're all different particles. They all live on Particle Island. And, people want to travel. The citizens want to travel between islands. But you see, there's sharks in the water. And while I'd love to see a shark, these are maybe dangerous ones. There's sea monsters, little M's flying around. Okay, so to be safe, what the people did is they built some bridges. Okay, so we got these bridges, and you know they really want it to be efficient, so we have one-way bridges. So if you want to go from Mole to Mass Island, you take this bridge, and if you want to come back, you take this bridge. That way, you know, we don't have any head-on collisions or anything like that. So what are these bridges? Well, you remember I've used the bridge concept before when we were doing unit conversions. For example, 1 inch equals 2.54 centimeters. That to me is a bridge between English and metric measurements. 1 kilogram is 2.2046 pounds. That's a bridge between pounds and kilograms. Okay, so I need some bridges. And so to go between Mole Island and Particle Island, we just have the definition of a mole. A mole is 6.022 times 10 to the 23rd particles. And so from that, I can make two possible conversion factors. Mole on top or mole on the bottom. Now, if I put that together, then what that means is if I had a number of moles, and I multiply by 6.022 times 10 to the 23rd atoms per mole, moles would cross off and I'd have a number of atoms. If I had a number of molecules, and I divide by 6.022 times 10 to the 23rd molecules per mole, the molecules would cross off and leave me with moles. So to get from Particle Island to Mole Island, I divide by Avogadro's number. To get from Mole Island to Particle Island, I multiply by Avogadro's number. Now I'm using this map analogy because I think it's a visual that helps some students, but truly, what I'd like you to get to the point is where you recognize labels and you say, well, gee, if I have moles, how am I going to get rid of moles? I got to divide by moles. I need something with moles on the bottom. I know how many particles are in a mole, so I'm going to use that per mole. Okay, what about this other way, going to Mass Island? Well, you know, this mole concept isn't just a random number. There's a reason that was chosen. It turns out that the mass of 1 mole in grams is numerically equal, or is numerically the same as the average atomic mass. Let me give you an example to make sense of that. If you look at the periodic table, I picked magnesium for my example, atomic number 12. Its average atomic mass is 24.30. That means if I have a sample of magnesium, the average atom is 24.30 atomic mass units. Some of them are heavier, some of them are lighter, but the average is 24.30. That's the mass of the average atom in atomic mass units. Now, what if I had a mole of magnesium? If I have 1 mole of magnesium, 6.022 times 10 to the 23rd magnesium atoms, I'd have a mass of 24.30 grams. It's the same number. Which allows me, if I go in the back room, get out a sample of magnesium, mass it out. If I mass out 24.30 grams, which I have a balance in here that can easily do that, I know how many atoms I have within, you know, my 3 or 4 sig figs. I have to measure this accurately, but I can figure out how many atoms I'm actually massing out. See, I don't have an atom counter. There is no tool for counting atoms easily, but I can measure mass easily. And that's why the mole concept is so fundamental in chemistry. And I really feel bad that I'm getting to this on the second last day for the seniors. It's not ideal, but at least we're getting to it. So what I'm going to do is turn that into a conversion factor, okay? If 1 mole of magnesium is 24.30 grams, well, I can make these two relationships. And I can use those relationships on my map, okay? Now, you notice I didn't put a particular number here. I said to go from Mole Island to Mass Island, multiply by the molar mass. I can't just put one number. Over here, I have a specific number. And this number is going to apply no matter what my substance is. Over here, for the mass, I have to go to a periodic table and I have to look at the specific molar mass of that substance. So magnesium has its molar mass, but aluminum has a different molar mass, and iron's going to have a different molar mass. And then if we get into compounds, you did some formula mass calculations yesterday, or 2 days ago, Monday. So if we had a compound, if I wanted to know if I was dealing with water, well, for water I have to add up the 2 hydrogen and the oxygen to find the molar mass of a water molecule. So let's just do a couple of practice problems and then set you loose. We're going to convert 7.35 moles of tantalum into atoms of tantalum. How many atoms would that be? So when I did conversion problems, we always write down what we're starting with. 7.35 moles of tantalum. And let's take a peek. Ooh. I want my map. There we go. Okay, I start out with moles, and I wanted to get to atoms. And atom is on particle island, so this says I'm going to follow this bridge, and I'm going to multiply by Avogadro's number. So, there's my moles of atoms. And I multiply by Avogadro's number because that's the number of atoms in a mole. And look, I got labels that can cross off. Please write your labels and make sure that they cross off. So moles cross off, I'm going to multiply those two numbers. Guess what? I'm going to get a big number. Well, if you are ever asked for an answer in the number of atoms or particles or molecules, you should be getting a big number. They're really small. Make sure you look at your calculator and get the exponential part. Okay, punch this in. You should be trying this. Make sure you get the same answer. 4.43 times 10 to the 24th atoms of tantalum. Now I've had students write down 4.43 atoms. Tell me how you get 0.43 of an atom. Explain that. Doesn't happen. You got to look at your calculator. Times 10 to the 24th. If you don't know what your calculator is saying, ask somebody who knows how to use your calculator to explain it to you. All right, let's try 74.32 grams of magnesium to moles. So, first thing we write down is a given, 74.32 grams of magnesium. Let's look at our map. We're starting with grams. That's a mass. We're starting on mass island. We're trying to get to mole island. So it says we're going to follow this bridge. We got to divide by the molar mass. Where do we get the molar mass? Periodic table. So we look up magnesium on the periodic table and we find out there's 24.30 grams per mole. So we're dividing by this. The per mole flips back to the top. Grams cross off. 3.058, 4 sig figs in this case, moles of magnesium. Okay. Hey, let's convert 8.505 times 10 to the 24th atoms of technetium to grams. I ran into Mr. Dieselhorst's wife in the grocery store yesterday, and we talked a little bit of science. She is, now I forget the title of her job, but she works in nuclear medicine, radiation, radioactivity, and she said technetium is what they use for a majority of their scans. Now technetium is an element that on our periodic tables is written in a funny outline because we don't find technetium naturally occurring on Earth. But we've produced it in nuclear reactors in amounts that we can use for practical medical diagnosis. Cool stuff. All right, 8.505 times 10 to the 24th atoms of technetium. We're trying to go to grams. So, I'm starting with atoms of technetium. I'm trying to go to grams. Now, do you see a bridge that goes from particle island to mass island? I don't. But can you find a route? Sure, I could go to mole island, and then I could get to mass island. That'll work. So I start out with my given, and I say, how do I get from particles to moles? Well, I'm going to divide by Avogadro's number, because that's the number of particles per mole. Atoms cross off. How do I get from moles to atoms? I'm going to have to look up the molar mass of technetium, Find it on a periodic table, 98 grams per mole. Set it up so that moles cross off. I'm going to be left with grams. All I got to do is the rest of the math. If you look at it, you got 10 to the 24th on top and you got 10 to the 23rd on the bottom. So a lot of that big number is going to cancel out. This is bigger than the bottom, and then we're going to multiply this, so it is still a sizable number. 1,400 grams of technetium. Limited to 2 sig figs because of that guy over there. Okay, so let's try one with a compound. What is the mass of 1.37 times 10 to the 22nd formula units of calcium chlorate? So I'm starting with formula units. Remember, that's kind of the fake molecule that we use for ionic compounds. So effectively, it's kind of like molecules. It's particles. And I'm going to mass. So I'm going from particles to moles to mass, just like the last one. Formula units to moles to mass. Starting out with 1.37 times 10 to the 22nd formula units. Be careful how you abbreviate that. Don't just use an F for formula and a U for unit. Doesn't look good. Now, calcium chlorate. We got to know what calcium chlorate is. And we've been, hopefully you've been looking at these ions and you've been studying these ions. And so we say calcium forms +2 ions, and chlorate is ClO3 with a -1. And so if calcium is a +2 and chlorate's a -1, I'm going to need 2 chlorates to go with 1 calcium. And we reason that all out. And we write it's Ca, parentheses, ClO3, close parentheses, 2. There's our formula. Now, to get to mole island, we just divide by Avogadro's number. That doesn't change. But to get to mass island, I need to know the molar mass of calcium chlorate. And that's where those formula masses come into play. That's 1 calcium and 2 chlorine and 6 oxygen adds up to 206.98 grams per mole. So bring that in, 206.98 grams per mole. Finish her off, 3 sig figs is 4.71 grams of calcium chlorate. Okay, there's effectively 6 different types of problems. You can start with mass and go to moles. You can start with moles and go to mass. You can start with moles and go to particles, and you can start with particles and go to moles. Or you can start with particles and go to mass and go to particles. Okay? And then we could have elements or we could have compounds. So we may have to do like this one and find out that mass. But I've shown you 4 examples. The rest is you need to practice a little bit, see if you can do some problems. My intent is that on Thursday, now Thursday is the last day with seniors, that on Thursday I'm going to ask you to do a couple of problems of formula masses and mole conversions. A couple problems, maybe 5 or 6 problems for a grade on Thursday. Now, if you get stuck when you're watching this today, please let me know, and I'll try to address your questions. Take care.